Theory of Computation, TOC. We can call this subject as formal languages TOC and flat. Same. Okay. This is one of the important subject in GATE, and minimum in every year minimum they will give 6 marks and 6 marks to 11 marks. So rarely 6 marks. On average minimum 9 marks, sometimes 10, sometimes 11. Okay, this is the weightage of the subject. And in this subject, the topics are finite automata. This is one topic. In this finite automata, what is a finite automata? What is DFA? What is NFA? And what is Mealy machine? What is Murray machine? And conversion between Mealy and Murray, vice versa. And elimination of epsilon moves and construction of DFAs. These all will come. And the second topic, regular expressions. In this, what is the regular expression for a given finite automata? If a finite automata is given, what is the regular expression? So expression to automata, automata expression, and based on that we do some questions. Then grammar. What is the definition of the grammar? Context-free languages. Push down automata, PDA. It is very important topic. And Turing machine. In this topic only we cover linear bounded automata, LBA, and decidability. Okay. So in coming to the GATE, we cannot say that out of these this is more important than the other one and that is the more next important to the compared to other chapters. We cannot say like that. Every topic is important. And one more thing, we cannot say that these many marks definitely will come from this topic or these many marks come from this topic, like that. So every topic and is important, and we cannot expect from which lesson how many marks will come. Okay, that depends. They can give, because from a particular subject you come from TOC. If this year if they give 10 marks question, 10 marks, next year they may give 11, next year they may give, and after that they may give 8 marks, like that. So every lesson is important. We must be very strong in concept. If we are strong in concept, whatever the question they give, we can attempt. First topic, finite automata. Before going to the finite automata, we will see what is an automata. An automata is a system where information, materials can be transformed and used for performing some functions without direct participation of a man. So whatever a man can do without directly going, those are called as automata. Example, or we can give the definition as it's a computer, like computer. It's a mathematical device. What is generally a computer? A computer which takes inputs and gives the outputs. Like that, we can give the block diagram for automata like this. It takes the inputs I1, let it be, this is I2, I3, so on. Let there are L number of inputs, IL. So generally the inputs we represent with sigma. You can represent with any letter, but usually we represent with sigma. Let this is I1, I2, IL. I1, I2, so on, IL means the number of inputs are 1 to L. Every time the number of inputs must be finite. We cannot take sigma equal to I1, I2, I3, so on infinity. It is not valid. You can take any number of inputs, maybe one input or two inputs or three inputs or so on, 100 inputs or 1000 inputs. But that number should be finite and non-empty set of inputs. Okay. These are the states Q1, Q2, so on. Let there are m number of states. So generally we represent the set of states with Q. Q1, Q2, Q3, so on, Qm. These are the number of states. The number of states are m. Here the inputs are L and the number of states are M. These number may be same, may be different. Anything can be more. Inputs can be more or states can be more. And these are the outputs O1, O2, so on, On. Generally the outputs we represent with delta, or you can represent any other letter, capital O like. So I am representing with delta, O1, O2, so on, On. Okay. These are the inputs, these are the states, and these are the outputs. These numbers can be in any manner. The inputs may be equal to outputs, or outputs may be less, or outputs may be more, or in states may be more, or states may be less. These numbers can be in any manner. There is no relation, no condition like that. The inputs must be equal to outputs, or outputs must be less than states or more than states. Not like that. Okay. And this is inputs, states, and outputs. Okay. Even though here m number of states, the automata at any particular time, if you take at a discrete time t, the automata will be in only one state. At a particular time, the automata will be in only one state. That state can be either Q1 or Q2 or Q3 or Q4 or any of these m states. Okay. Let the machine is in state Qi. Qi is something Q1, Q2, Q3 or like that. Okay. At present, the automata is in state Qi, and then how the next state will be changed. So the next state of the automata depends on the present state, means Qi, and the present input. So whatever the input of these symbols. Okay. So let the input is I, J, let it be. So depends on this input and this state, the next state will be decided. The next state may be the same state, or it may go to Q1, or it may be Q2, or maybe other state, or it may remain in the same state. It doesn't mean that after taking the input, the machine has to change the state. Not like that. The machine may change the state or may remain the same state. Okay, but purely it is the next state depends on the present state and present input. Okay, that is about state relation. Now, output relation. This output can be depends on only on input. Means like this. Means suppose the input is 0, if it gives output A, when input 1, it may go to different output B. So the output depends only on input, or the output depends only on state. Output depends only on state. That means here it is independent of the input. Here it is independent of the state. So when the output depends only on state, that means if the machine is in Q1, if it gives 0, if it gives some output, let it be A, and when the state is Q2, it may go to different output, maybe B or C or something else. Okay, or so the output can depends only on input, or the output can depends only on state, or the output can depends on both input and state. Depends on both input and state. That means if the machine is in Q1, if input 0, if it gives A, when the machine is in the same state but different input, it may go to different output. At the same time, if input 1, if we change the state, the output will be changed. So clearly the output can depends only on input, in that case independent of the state, or only on state, in this case independent of the input, or it can depend on both input and state. This is okay. Next, if the output depends only on input, we call it as automata without a memory. Okay, and these two cases, if the output depends either state only or both input and state, it is called automata with finite memory. Guys, remember this point, an automata does not have the memory. Okay, it doesn't have the memory, even though output depends on state or only state or both input and state, we call it as automata with finite memory. Okay, so we'll discuss about this, what is finite memory, after some time. Okay, so this is next. Okay, if the output depends only on state, we call this as Moore machine. And if the output depends on both input and state, we call this as Mealy machine. This is Moore machine and this one is Mealy machine. Okay, this is a general talk about automata. Okay. Now we will see the complete definition of the finite automata. In the previous block diagram, we have seen the elements that an automata will have the inputs and states and outputs. State relation will be there. It means at a particular time, if it is some state, after taking some input, it go to the next state, or it may be in the same state. And output relation, how the output can be generated. So these all we have seen. Now, what is a finite automata? It is a phi tuple. It is a phi tuple. Finite automata. We can represent with it's a machine, so we can use the M to represent the machine, or you can use with any other symbol. So I'm taking as M, stands for machine. It is a phi tuple Q sigma del Q naught F. What is Q here? It is a finite non-empty set of states. Finite non-empty set of states. Okay, means finite. What does the meaning of the word finite? You can take any number of states. You can take one state or 2 or 20 or 100 or 200, whatever. But whatever the number of states we are taking in this automata, that number should be a finite. Example, Q equal to Q1, Q2, Q3. Example, Q equal to Q1, Q2, Q3, so on. I can take up to 100, or I can take up to 200, or I can take up to 1 lakh. You can take any number of states, but you cannot write like this. What does the meaning of this? Q equal to Q1, Q2, so on, Q to 100 and so on, infinite. So not valid. So when we are constructing some automata, we can take any number of states, but that number of states should be a finite number, means countable number. Okay, next. And this one, sigma, it is finite set of inputs. Okay, means here also you can take any number of inputs, but that number should be finite. I cannot take the sigma equal to 0, 1, 2, 3, so on, infinite. No, it is invalid. You can take sigma equal to 0, 1, 2, 3, so on, 100 or 1000, like that. So the whatever number we are taking, that number of elements should be the finite. And this one, transition function. Transition function. This transition function describes the change of the states during a transaction. I repeat, the trans function describes the change of the states during a transaction. What does the meaning of this one? Suppose a machine is in some state, let it be in Q1, and if we take some input, let it be 0, based on this input and this state, the next state will be decided. So, in which state, on which input, what is the next state? These all information will be defined given in transition function. So, the next state depends on the present state. A state is one of the element from Q, means set of states, and depends on the present input. Input is one of the element from sigma. So, it takes a state and input. Based on these two, the next state will be given. The next state may be the same, or it may be a different state from this. So clearly that is also, the next state is also one of the state from Q. So that is the mapping of trans function. We can say we can write like this. It takes a state and input gives the next state. This is the mapping. Next, even though there are hundreds of states, every time the machine has to start from some initial state. That is called as starting state. That starting state we must define. It may be Q0, it may be Q1 or Q2 or any state. There must be compulsory starting state should be defined. Example, Q0 we are taking as initial, so starting state. It is initial state, or you can call it as starting state. Initial state is one of the state from Q. So Q0 belongs to Q. And remember this point, an automata may have more than one initial state. I repeat, compulsory one initial state has to be there. And at the same time, an automata may have more than one initial state. Suppose if there are 100 states, out of 100 you can take 2 initial states or 20 initial states, whatever. So clearly, an automata may have more than one initial state. This I will give you example with proof when we discuss about properties of regular languages. Okay. So compulsory in one initial state has to be there and can be more. And this one, set of final states. Final states. Okay. So F subset are equal to Q. That means out of these states, a final state may be there, may not be there. It is not compulsory that every automata must have final state. No, there may be a final, may not be a final. If there are final states, that number can be 1, means there can be only one final state or 2 final states or more than one final state. Okay, or it may be empty also. See, clearly an automata may have or may not have final state. If they have, it can have 1, it can have more than 1. So this is the complete structure of the finite automata. Non-empty set of states, set of inputs. Inputs also we can take empty. Without taking the inputs also we can define the automata. Okay, we see an example. And trans function, it describes how the state will changes, that one. And initial state may be more than one, and usually we deal with only one initial state in entire this topic. Okay, and this subject, and this one, set of final states may be 0 or more. Okay, you can copy this one. Now we have seen the structure of a finite automata. Now we will see the representation of finite automata, how we can define, how we can represent a finite automata. So we can represent the finite automata like this by transition diagram. Okay. Representation of finite automata by transition diagram. Okay, in finite automata, we represent the states by circles. In the diagram representation, each circle represents a state, and the initial state will be represented by an arrow pointing towards it from outside. So whatever the state having an arrow towards it, pointing towards it from outside, it is called as initial state. Okay, and those states are having two concentric circles, they are called as final states. Okay, here the states are q0, q1, q2, three states, and this one is initial and this one is the final. Okay, and here there are some directed edges. These directed edges are labeled with some inputs. Look at this. Here the states are Q0, Q1, Q2. Initial state is Q0 and the final state is Q2. And these directed edges are labeled with some inputs. So the whatever the labels are there, they are called as inputs. So here see, and overall the labels are only 0 and 1. So the inputs are 0 and 1. States are Q0, Q1, Q2. Okay. What does the meaning of this directed edges? Okay. Suppose the machine is in Q0 state. Suppose the machine is in Q0 state. And if input 0 is given, the machine changes to state Q1. That's the meaning. Okay. Means if the machine is in Q0, if input 0 is given, after taking this input 0, the machine changes to the state Q1. That's the meaning of this one. Okay. One more thing, the input string, whatever, it is a combination of the input symbols. Okay. So if this is the input string, which is something, an input alphabet. Suppose if input alphabet is sigma, it is 0, 1, then this is the string and each symbol is either 0 or 1, 0 or 1, 0 or 1, 0 or 1, you like that. Okay, if this string is given to the finite automata, every time the finite automata scans the input string from left to right, it starts from the leftmost symbol, means from this, and it scans the string from left to right, starts from leftmost symbol, and every time it scans only one symbol. Example, if this is first symbol, it scans, then at a particular time state, after scanning this input symbol, if we say go to next state, then it will go to next state. If we say remain in the same state, it will remain in the same state. Example, in this state, if 0 is the input, it goes to Q1. So when the machine comes to this, it goes to Q1. Suppose in this state, if this input is 1, what we are saying there, we define that it remains in the same state. So if this is the one input symbol in this Q0 state, it will go to next input symbol and remains in the same state. Means here also the the state is Q0 only. So every time it scans the input string one by one. This first, then this, then this, then this, like that. So it scans the input string from left to right, starting from leftmost symbol, and every time it scans only one symbol, not more than one symbol. Okay, this is about scanning of the input string. So this is the example of a finite automata by transition diagram. So states are Q0, Q1, Q2, initial is Q0 and the final state is Q2, and inputs are 0 and 1. Okay, and if the machine is in Q0, if input 0 is given, it goes to Q1 state. At the same time, if the machine is in Q0, if input 1 is given, it remains in the same state. Like that, Q1 and 0, it comes back to Q0, Q1 and 1, it goes to Q2, Q2 and 0, it remains in the same state, Q2 and 1, it goes to Q0. So this is by transition diagram. The same automata we can represent by transition table. By transition table. In transition table, there will be two columns mainly. One is present state column and the other one is next state column. So present state, the other one is next state. In next state, for every input symbol there is a column, separate column. What are the inputs here? 0 and 1. So for 0 there is a column and for 1 also there is another column. Okay. So this is the structure of a table. So present state and next state under, for every input we will take a column. Okay. And what are the states here? For the same finite automata, we are writing the table. So the states are Q0, Q1, Q2, and the initial state will be represented like this, an arrow pointing towards it, and Q2 is the final. The final state we can represent using star like this, or the same we can represent by circle like this. So some textbooks, if they write star, that indicates it is a final state, or we can use the circle like this also. Okay, now in Q0, if input 0, what is the next state? It's Q1. Q0 on 0, Q1. Q0 on 1, Q0. Q1 on 0, Q1 on input 0, Q0. Q1 on input 1, Q1 on input 1. Where it is going? It's going to Q2. Q2 on 0, it's Q2. Q2 on 1, Q0. So this is another way of representing the automata, that is by transition table. The same we can represent with another way, that is by phi tuple, means the complete structure we write here. So guys, what is the phi tuple? Earlier we have discussed. So it will have states Q, sigma inputs, and trans function del, then initial state Q0, and then F set of final states. Okay. Here, what are the states we are using? This, okay, Q0, Q1, Q2. This is a Q, capital Q. And sigma. What is sigma? Here, what are the inputs here? 0, 1. This is sigma. And del, that is transition function. We define later. What is initial state? Initial state is what? Q0. And the final state, we are taking only one final state. So that is Q2. If we take more than one final state, then we write them. So this is Q, set of states, sigma, set of inputs, trans function, initial state, and the final states. Okay. So everything we have defined: states, inputs, trans function, initial state, and final state. But we didn't define the trans function completely. So means in which state and which input, what is the next output state, that how we have must define. So we define that here. Q0 on input 0. Q0 on input 0. What is the output state here? It is Q1. So Q0 on 0 is Q1. Next, Q0 on 1. Q0 on 1. It remains in the same state. Similarly, Q1 on 0. Q1 on 0, it is Q0. Q1 on 1. Q1 on 1, it is Q2. Q2 on 0. Q2 on 0, it is Q2. Q2 on 1, it is Q0. So this is the diagrammatic representation. This is table representation. This is with phi tuple representation for the same automata. So we can represent these ways. So you can copy. Okay, so after this we will see what is the advantage of finite automata. Why should we construct this? Okay, finite automata mainly we will see this application in comparative design. In comparative design there are different phases, and that very starting phase lexical analyzer, that is lexical analysis. In lexical analysis we use this, okay, to okay. So finite automata, the main advantage is used to accept regular languages. Okay, here finite automata is used to accept regular languages. Okay, this statement is okay. So a finite automata, that means it accepts a language called regular. Then what is the meaning of this? Or you may get this doubt. Which language is regular? Here I told that finite automata is used to accept regular languages. You may have idea what is a language, but you may not know what is a regular language. So, which language is regular? So, the same statement I write like this. A language is said to be regular. A language is said to be regular if it is accepted by finite automata. Okay. Here what I said, finite automata is used to accept regular languages. So based on that, finite automata accepts regular. That language is means I repeat. Sorry, I repeat. Finite automata is used to accept regular language. That means whatever the language accepted by finite automata will be called as regular, because finite automata accepts only regular. So every language accepted by finite automata will be regular. So here, how can we say that a language accepted by finite automata? We will see that. Before going to this acceptance of finite automata, okay, acceptance of a language by finite automata, we will see what is language first. What is a language? Or okay, now first of all I'll give you sigma. We'll go from input alphabet, that is sigma. Input alphabet. Generally input alphabet we represent with sigma. Okay, what is input alphabet? Actually for this input alphabet there is no prescribed definition, but it can have anything, but it must have a finite, means the countable finite number of elements. Example, if I can take 0 1 means it is a binary, okay, set. Or I can take sigma equal to A, B, C, D, so on, Z. So all alphabetics. Or I can take only few of them, sigma equal to A, B, C, like this. Or sigma equal to plus minus, multiplication and division. Okay, so you can take any elements, but that number of elements should be finite in sigma. Okay, this is about input alphabet. Now, what is the meaning of this sigma power k? It is set of all strings over the combination of sigma of length k. I repeat, sigma power k is set of all strings over sigma, means over this, suppose sigma is 0 1, over the 0 1 or the combination of 0 1s having set all strings of length k. Okay, example, I am taking sigma as 0 1. Okay, now what is sigma power 0? Sigma power 0 is set of all strings over sigma of 0 length. Okay, so here 0 length is a string, it is empty string, that is epsilon. Epsilon is a string of length 0, its length is 0, and epsilon can be written from whatever the input alphabet sigma, you either you take 0 1 or a b c d or plus minus, so every over sigma epsilon is the length of string. Okay, in length of 0 is a string of length 0 over sigma. Now, what is sigma power 1? It is 0 comma 1. And what is sigma power 2? It is any combination over sigma of length 2. Here sigma power 1 is over length 1. What are the length 1? 0 and 1. And sigma power 2, it is all combinations of zeros and ones, 0 and 1s of length 2. So what can be this? 0 0 and 0 1 1 0 1 1. These are the substrings. Sorry, these are the strings over sigma of length 2, sigma square. If it is sigma cube, so it is all strings of length 3 over 0 1. Example, 0 0 0 0 1 0 1 0, like this, 0 1 1 and 1 0 0 1 0 1 1 1 0 1 1 1. Okay, these are the strings. Okay, 1 2 3 4 5 6 7 8. Yes, see, we want the length 3. Sigma cube means it is all strings of length 3. What are the inputs here? 0 and 1. So here you can take either 0 or 1. So you can fill with two ways. You can fill this place with two ways, either 0 or 1. And again this can be 0 or 1. You can fill with two ways. Again 0 or 1. Fill with two ways. So 8 strings will be there. So these are the 8. So I think you understood this one. So sigma power k. So finally sigma power k is the set of all strings of length k over sigma. Okay. Next, we have seen what is input alphabet. Now, what is a string? What is a string? Generally, we represent the string with W. If sigma is input alphabet, suppose 0 and 1, then string W we generally represent. A string is, we use the notation sigma star. W belongs sigma star. So what is the exact definition of string? A string is any finite combination of 0 and 1 over, or we can say any finite combination over input alphabet sigma. Okay, so you can take a length 0 or length 1, length 2, length 3. You can take any number, any length, but that length should be a finite. Example, what is the difference between finite and infinite? A string is this one, over 0, 1. So 0, 1, 0 is a string, yes. And 1, 1, 0, 0 is a string, okay. And 0, 0, 0, 1, 1 is a string. And similarly, whatever you can write over 0 and 1 will be a string. Example, see this one, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. If I write like this, infinite length, so this is not a string. You can take any combination over input alphabet, that length should be a finite, means that is should be a finite combination. Okay, next. So we have seen what is input alphabet. No definition, but it must have a finite number of elements. Then string. A string is any finite combination over input alphabet. Next. Language. Generally, the language we represent with L, capital L. A language is set of strings W1, W3, W4, W1, W2, W3, W4, so on. So on. See, I repeat. A language is set of strings. Okay. Like L equal to W1, W2, W3, W4, W5, so on. So, are they finite or infinite? A language can have any number of strings. It may have a finite number of strings, or it may have infinite number of strings. Language can be infinite. Okay, but string cannot be infinite. Whatever the string we take, okay, that should have a finite length. Okay, and sigma also must have finite number of elements. Sigma is set of elements, should be finite. String is any combination over sigma, should be finite. A language is set of strings. Those strings, it may have finite number of strings, or it can have infinite number of strings. Okay, this is about alphabet, input alphabet, string, and language. Okay, here we can write like this. It may have finite, or it may have infinite number. Okay, next we will go. Actually, we came from a finite automata is used to accept regular languages. So before going to that concept, I told you what is a string, what is input alphabet, what is a language. Now we go back to the previous one. Acceptance by finite automata means how we can say a string is accepted by finite automata. Okay, first I'll give you one example of finite automata, then I'll tell you how to accept a string. Okay, this is the finite automata. What are the states here? Q0, Q1, Q2. What is the initial state? Q0. What is the final state? Q2. And what are the inputs? 0 and 1. So in Q0, if input 0, it is going to Q1. Means the machine changes from state Q0 to Q1. And if the machine is in Q0, it remains in the same state when input 1 is applied. So the remaining you can understand. Okay. When do we say a string is accepted? A string, generally we represent with W. belongs to sigma star means it is a combination of input symbols, a finite combination. A string W belongs to sigma star is said to be accepted by finite automata. Is said to be accepted by finite automata if it starts at initial state. What is the initial state here? Q naught. It has to start from initial state and terminates at some final state. Here I am using the word some final state. Means an automata may have more than one final state. By starting at initial state, when the machine stops, if it stops at any of the final state, suppose there are more than one final state, if it can stop any of them, if any final state, then the string is said to be accepted. So by starting at initial state, so initial state is Q naught. By starting at initial state, if the machine stops at final state, okay, so QF. Then what is QF here? QF is a final state. By starting at initial state, if it stops in a final state, then we say that string is accepted. Here one more condition is there. Example, if this is the string, okay, the total string has to be scanned by the finite automata. It has to start from initial state and the string must be scanned completely. No symbol should be left. The string has to be scanned completely, and when the machine stops, it must stop in one of the final state. That is the definition of. So by starting at initial state, if it reaches the final state and if the string is completely scanned, then we say the string W is accepted. Okay. So for this finite automata, we see one example. Okay. So here I'm taking one example. 1010 is the string accepted by the given finite automata. So here we must start from the initial state. Okay, I am starting from initial state. What is initial state here? Q naught. Now look at this. Q, every time the string will be scanned by the finite automata from leftmost symbol to the right, from left to right, and start from leftmost symbol. So here what is the string here? 1010. Okay, it starts from initial state. Okay, Q naught on 1. What is the next state? Q naught only. It comes to this one. And Q naught on 0. Q naught on 0. Where it will go? It goes to Q1. Now in Q1, what is the input state in symbol 1? It goes to Q2. Then Q2 on 0, it remains in the same state. So finally it has reached the Q2. I repeat, every time the string will be scanned, we can write like this: Q naught 1010. First symbol is 1. This one. This is the first symbol. And at present it is in Q naught. So what will be the Q naught on 1? The machine remains in the same state only. Okay. Already it has scanned 1. So what is the remaining input string? 010. Okay. Now the machine is in Q naught. Input symbol is 0. Q naught on input 0. What is the output state? It goes to Q1. Okay. Q1 and the remaining input string is 10. Now the machine is in Q1 state and present input symbol is 1. So Q1 on 1. What is the output state? It goes to Q2. Q2. What is the next input symbol? The remaining input string, it is 0. Now Q2 on 0. Q2 on 0. The machine remains in the Q2 on 0. The machine remains in the same state and the input string is over, empty. So when the string is empty, the machine stops. So here the machine has scanned the string completely. The machine has scanned the string completely, and finally it has stopped in Q2, and Q2 is a final state. Therefore, Q0, comma 1010 is Q2 and Q2 is a finite state. Therefore, we say 1010 is accepted. If you want, you can copy this one. Okay. We see one more example. Look at this string. Every time it has to start from initial state only. I am taking 0 1 0 1 0 1 0 1 Q0. From Q0 0 comes, it goes to Q1. Q1 on 1, it goes to Q2. Q2 on 0, it remains in the same state Q2. Q2 on 1, where it comes back to Q1. So it reached the Q1. Is Q1 is final or non-final? It is a non-final state. It is a non-final state. Therefore, 0101 is not accepted. Whereas 1010 is accepted and 0101 is rejected, or you can say not accepted. This is what acceptance of a string by finite automata.